Okay, next we'll discuss, well, eventually formal charges. Again, we're not going to cover vibrating bonds and the greenhouse effect right now. We'll cover a little bit of that later in 105 and 6. Um, I do want to mention, before getting into formal charges, I will discuss a few different ways we can tell um, when there are structures that are not what we expect by the way we first look at Lewis structures. One is looking at resonance structures. Not all molecules can be represented accurately by a single Lewis structure. Our way of drawing the way molecules act doesn't always, cooperate with what nature wants to do. So sometimes two or more structures may be drawn with identical formal charges. Sorry, we'll discuss formal charges in a bit. That I shouldn't have needed to have that in here right now. But anyway, now basically there are two. What this means is there are two or more structures that we don't know which one is the true structure. So in this case, the actual structure is actually an average of all of the similar structures. And these are called resonance structures. So let me show you that. I'll work this out. I think it's easier to see. Again, we'll take ozone. Get my pen over here, which is O3. Excuse me. So ozone, you should know, has 18 valence electrons. Draw the Lewis structure. We'll start with this. One way to start it is maybe a good thing for you to just to practice draw the Lewis structure for ozone first if you haven't already done that, and then we'll start the structure. So I would start this way. Now I'm going to label each of these oxygens because even though they look identical, they are different oxygens, and that's going to show us oxygen 1, 2, and 3 what we need to do. Now, of course, the octets on both the outer oxygen atoms are satisfied. The outer atoms are happy. The inner oxygen has only 6 valence electrons and wants 2 more, so it needs to get one of its neighbors to share. And even though it looks identical, we have 2 different options. This oxygen could agree to share 2 electrons, or this oxygen could agree to share two electrons. And you might think, what's the big deal? But let me show you. In one case, we get an oxygen-oxygen double bond between oxygens 1 and 2, and a single bond here. Put our electrons in. That's our Lewis structure. If oxygen 2 and 3 form a double bond, then we get this formed. Again, this is oxygen 1, 2, and 3. And you might think, well, all right, what's the big deal? They're mirror images of each other. What does it matter which one is which? Well, the problem is we can use spectroscopy. We can use different types of techniques to tell what type of bond is present. These techniques actually are what was in the last section we kind of skipped over. I will mention that if you've ever seen something like a tuning fork, you hit a tuning fork, it vibrates at a very specific frequency. Well, if you set a tuning fork down, or you're just holding it, and there's a speaker nearby that's vibrating at that frequency, then it will actually start vibrating. It will absorb that energy and start vibrating. Well, bonds will do the same thing. Bonds are not rigid structures. They almost act like springs. They vibrate, twist, rotate, depending on the type of bonds formed, atoms connected to it, all sorts of things. And so they can absorb different wavelengths of energy. So we can use this to tell what type of bond is present in a given molecule. When we look at spectroscopy, though, what it tells us is we don't have one double bond and one single bond. It tells us we have 2 bonds that are identical. And they're somewhere in between double bonds and single bonds. They're like 1.5 bonds, which doesn't make sense to us in a way. But what that tells us, for right now, is that the actual structure is somewhere in between these 2 structures. And we denote this by putting a double arrow between these 2 guys, and these are resonance structures. Where the actual structure of the ozone molecule is somewhere in between these 2 structures. Other cases like this, but this is what happens with resonance structures. We have 2 cases where these 2 molecules look like they're identical. These 2 Lewis structures look like they're identical representations of the molecule, but the real structure is somewhere in between. If you want to try to understand it, we'll go through this in more detail in 105 and future chemistry courses. But We mentioned that atomic orbitals merge to form a molecular orbital. Well, in this case, what happens is the atomic orbitals of all three oxygens merge to form one long molecular orbital that encompasses all three atoms. So the electrons actually hang out, the extra two electrons hang out somewhere between all three atoms. So you get this distributed electronic charge, or the distributed electrons, and we get effectively a 1.5 bond between each of the atoms. So that's what this is showing. It's trying to show the same with ozone. Let's see. These are the two Lewis structures. The actual structure is somewhere in between. What this is showing is the length of the bonds. We can use the length of the bonds to really give an idea of what type of bond is present. Double bonds are shorter than single bonds, so we would expect if this were a single bond and a double bond, the two bonds should be the same length. I'm sorry, the two bonds should be different lengths. Since they're the same length, the lengths are in between what we expect for oxygen-oxygen single and double bonds, we know that this is somewhere in between what we expect to happen. It's showing the same thing. This is another molecule you'll deal with a lot when you get to organic chemistry. It shows that there are, with this benzene ring, we can have the double bonds, between these carbons or between these carbons. They can be switched back and forth. But in real life, these 6 bonding electrons of these double bonds that are shifting around, the extra 6 electrons, are being evenly distributed between all the atoms, all the carbon atoms, and so the actual structure is somewhere in between this. So the benzene ring is often denoted as the hexagon with the circle in between, in the middle, just to denote this resonance structure. So other examples you can play with, we give you a little practice. We'll deal with more of this later on. So this is what we alluded to in 4.6. We need to discuss what is formal charge. When we looked at earlier, back there, if you remember with CO2, we discussed 2 possible Lewis structures for carbon dioxide. One was this, and the other had a oxygen triple bond. And how do we know which one is correct? Well, formal charges let us know which one of these is the stable or the preferred structure. So this wouldn't be the resonance structure. We look at, we can actually look at this and tell what is the preferred structure. So that's what formal charges do for us. And this is another case we're trying to decide which is the preferred structure in this case. The formal charge is determined by the difference between number of valence electrons in the free atom and sum of lone pairs and half of bonding electrons in a molecule. That sounds really awkward. It's actually very, very simple. Let me abbreviate this in a little bit simpler form. Formal charge is the valence electrons in the neutral atom minus unshared electrons minus 1/2 of the bonding electrons. We can abbreviate this, and again, I should stress this is formal charge for each atom, not for the overall molecule or ion. You also see abbreviated valence electrons minus bonding electrons minus 1/2 of, sorry, she messed myself up here. Should pay attention. Unshared electrons minus 1/2 of the bonding electrons. I'll show you visually where this comes from so it makes a little more sense, I think. If you understand it, then it's a lot easier than trying to memorize the equation. You can always figure out the equation if you understand what the concept is really talking about. What it's really telling us is the effective charge around each atom. I should mention here, I think it's in the other slide, but formal charges of all atoms must add up to the overall charge of the molecule or ion. So if we have a molecule, all the formal charges of the individual atoms have to add up to 0. If we have an ion, the formal charges have to add up to the charge of that ion. So let's go back up here. So the formal charge, I'll label this oxygen 1 and oxygen 2, but in this case they're the same thing. Formal charge of, say, oxygen 1 will be the number of valence electrons that oxygen normally has. So, of course, it normally has 6, minus the unshared electrons around the oxygen. It has 4 unshared electrons, so minus 4, and minus half of the bonding electrons. There are 2 bonds, 4 bonding electrons, so 1/2 of 4 gives us a formal charge of 0. Formal charge of a carbon, well, carbon normally has 4 valence electrons. When it's neutral, it has no unshared electrons, and half of its bonding electrons, it's got 4 bonds, so 8 electrons, and so it has a formal charge of 0. Formal charge of oxygen, oops, more space there. Formal charge of oxygen 2, again, equals 0. Same thing as here, the exact same. So, and down here, oxygen 1 and oxygen 2. If you have confidence in this, maybe you should pause the video and work these out for yourself first. Formal charge of oxygen 1. Again, oxygen normally has 6 valence electrons. Minus, this one has 6 unshared electrons around it. Minus 1/2 of the 2 bonding electrons gives it a formal charge of -1. Formal charge of the carbon still is 4 minus 0 minus 1/2 of 8 bonding electrons, so it's still going to be 0. Formal charge of oxygen 2 be 6 minus 2 unshared electrons minus 1/2 of 6 bonding electrons. Excuse me, gives us a formal charge of +1. So first, all these charges add up to 0. That's a good way to double check. But formal charges would prefer to be as close to 0 as possible. And we'll discuss some rules here in a bit to know which is favored, but formal charges would like to be 0. And in general, the more electronegative atom would want to have the negative charge. It has a stronger attraction for electrons, so it makes sense that that's the one that would have the negative charge on it, or the negative formal charge. Alright, so if we look at this second molecule, just to show you what formal charge really means, it helps you visualize it. With formal charge, we're comparing the number of valence electrons of an atom when it's by itself and it's neutral to how many are immediately around it when it's in this molecule, to see what the effective charge is around that atom itself. So for this oxygen, oxygen 1, we basically take the bonding electrons and split them in half. They're shared between these 2 atoms. And with these bonding electrons, half the electrons go with the oxygen, half the electrons go with the carbon. And the unshared electrons are tied just to that atom. And that's what this equation is telling us. So oxygen normally has 6 valence electrons when it's by itself, when it's neutral. Here it has 6 unshared electrons, these 6 that are tied directly to it. And it has 1/2 of the 2 bonding electrons, which gives it 7 electrons around it now when it normally only has 6. That's why it has a -1 charge. The carbon, again, the bonding electrons, we have 4 bonds, 8 bonding electrons, half go with carbon, half go with the other atoms, with the oxygens. Carbon normally has 4 valence electrons, it has 4 here, so it's electrically neutral. And this other oxygen over here, we split the bonding electrons in half. This got, 1, 2, 3, 4, 5 electrons immediately around it. It normally has 6, so therefore it has a +1 charge. This is what the equation means. I think visualizing it helps it make more sense. Hopefully helps you understand the equation better versus just memorizing, because when people just memorize, it's easy to get tripped up. So go back to, when you look at formal charges, go back to what makes sense. Go back to what this is really trying to tell us. So this is another case. I'll let the next slide will show you. With these three cases, we want to find which is the best, the most stable form of this molecule. And this is again a case where you might think, are these resonance structures? All we're doing is shifting electrons around. So could they be? Well, if the formal charges are all identical, we can't tell which is preferred. Then yes, they would be Lewis structures. But this is showing the formal charges of each individual atom using the same thing we just went through. So you can see. Again, formal charges is in the bottom. They're working out the steps for you. Before I did, I should have said it might be good for you for practice. Take each of these structures, work out formal charges for each atom for each of these structures, and see if you can figure out which is best. Again, having formal charges of as close to 0 as possible is preferred, and the negative formal charge should be on the more or less negative atom. So if we look down here, looking at formal charges, you can double check your work here. First of all, we have these three formal charges, and these three, they are very similar, a +1, a -1, and a 0. So we'd like to have zeros for everything, but we don't have an option. In this case, we have -2, +1, and +1. Well, that's not going to work. This is farther from 0, so this would not be a preferred structure because we have something and we have a +2 charge, or sorry, -2 charge versus just plus or minus ones. In addition, we have, oxygen is the more or less negative atom, and oxygen has the +1 charge, but here the nitrogen has a negative charge. That doesn't make any sense. The more or less negative atom should have the negative charge, if at all possible. And that leads us back to these two cases to decide which is preferred. They look almost identical. The difference being that in both cases the central nitrogen has a +1 charge, so that doesn't matter. It's the same thing in both cases. So we have to decide, should the negative charge be on the oxygen or on the nitrogen? So look at the periodic table. Oxygen is farther to the right, so it's more or less negative. So the negative charge should be on the atom that has a stronger attraction for electrons, which means that this is the preferred structure. So a lot of people might like this structure in the middle just aesthetically because we have nice symmetric bonds, but the structure on the left would be preferred because we get the negative on the more or less negative atom. So it says that's the more stable charge. And you get more practice here. So as I said, the more or less negative atom should have the negative charge, and formal charges closest to 0 are going to be preferred. Now here I want to mention that there are exceptions to the octet rules. We'll cover these more in 1 and 5 and 6. But there are some oddities that will happen, so I just want to make you aware of these cases so we don't say that these are hard and fast rules with Lewis structures. And just at least touch on why we have these exceptions. Some electrons have odd numbers of electrons. They're called free radicals. They're often very reactive species because they don't have full octets, but they can be stable under certain conditions. And you can have what are called expanded valence shells. You can have atoms that have sometimes much more than an octet of electrons around them. One example is SF6. And let's look at these, and you can use formal charges to actually help explain why these happen. Look at nitric oxide. Well, nitrogen only has 2, 4, 5, 6, 7 electrons around itself. Oxygen does have its octet, but nitrogen does not. Again, that's though because nitrogen has a formal charge of 0. Well, I should have put that in the middle. Can we split these bonding electrons in half to count formal charges? Nitrogen has, 1, 2, 3, 4, 5 electrons around it. The neutral atom has 5 electrons around it, so its formal charge is 0. Oxygen, the same thing. It has 6 electrons around it. Again, looking at it the same way, or using the equation either way. It's actually good to do both to practice to help try the concept home better. And so both atoms have formal charges of 0. So that's one reason that makes this stable, even though it can be a very reactive species. It is a stable molecule until it finds something to react with to get to some more stable molecules. And so that's what free radicals are: odd number of electrons, atoms or molecules, and they can be very, very reactive because even though they have formal charges of 0, they like to get to an octet if they can. So they're stable to a point. Expanded shells I will mention briefly just because they can happen also. This usually happens to elements in the third period or lower, especially well, in particular the p block, because you get the d orbitals involved. And we've alluded to the d orbitals do funny things. That's why we cannot predict what charged ions the transition metals will form. And for the same reason, when these d shells can get involved with the nonmetals, they can cause nonmetals to actually get an expanded octet. And this we'll touch on in 1 of 5 and 6 when we look at hybridization. But just wanted to at least mention that. And last thing I'll mention briefly, just to make you aware of it. I'm not going to ask you this on the exams, but right now, but you should be aware of this. Bond length depends on the type of bond being formed. Single bonds are longer bonds, double bonds are a little bit shorter, triple bonds even shorter, and that's what this is trying to allude to. Single bonds, two shared electrons, the atoms are farther apart. When they start sharing more electrons, they end up getting tied closer together. Now, again, it's not hard and fast, not set in stone. The length changes depending on the atom that's involved. But this shows for hydrogen peroxide, we have the oxygen-oxygen bond. It's longer. For double bond, for O2, is shorter. And as we mentioned earlier with the ozone example, the length of the oxygen-oxygen bond in ozone is between the single and double bonds. So that's why we know it's like between a 1 and 2 bond for ozone. Cause that resonance structure. And the other thing I'll mention, which you'll pick this up in more detail 1 of 5 and 6, is bond order. We still allude to that sometimes. Really straightforward. Bond order is just single bonds have a bond order of 1, double bonds bond order of 2, triple bonds bond order of 3. So that's it. Pretty straightforward. And that's it for this chapter. And if you have any questions, let me know.